Okay, it's 1 o'clock, so let's go ahead and get started. So first, thank you everybody for taking some time out of your day to come and listen to this. So today we'll be just giving, again, a brief overview on Green Bank Observatory operations. For some of you, you'll have heard much of this before, but I'll update as to where we are with things. After that, we're going to move into our focus on the Mustang-2 system, and we'll have both Brian Mason and Charles Romero talking about early science with Mustang-2, and then looking into the future where Mustang-2 will be. As a reminder with all of this, two things. First off, this talk is being recorded for those people that are unable to attend it, so please be aware of that fact. Second, if you have any questions during this, please just use the chat. When we see the questions in the chat, we will pause and read out the questions as we can. Thank you. So, status of Green Bank. First thing to step through is just, of course, the status of West Virginia and where the state itself is. West Virginia is in the process of a gradual reopening of businesses. It's not a full reopening. There's a lot of restrictions still in place, particularly in terms of the number of people, as well as just the procedures and safety that has to be used as you're opening up. The state of West Virginia continues to have positive cases around the 2% mark. So this is required for the opening of businesses. It has to stay underneath 3% or the governor will start to restart things. Green Bank Observatory has been operational as an essential business within the state, and that has allowed us to keep skeleton crew on site and much of our staff working from home. The good news of all of that is we have remained operational, at least no issues due to COVID since any of this started. 24 hours a day, 7-day operation of the GBT. We are now into, I would say, semi-routine receiver changes. Our general maintenance is fairly routine as well. The processes take a little bit longer, as you can see in the image on the slide. There's a lot of PPE we have to take into account. A lot more distancing within the individuals, which can slow things down, but nonetheless, we can handle most maintenance for the site. So that's been fantastic. Similarly, we're starting to ramp up the work on site. We've had a few people in our machines shop to start working, for example, on our wideband feed and on the LASSI project. And we're starting to slowly bring some of the staff who simply aren't able to work from home because of the tools that they need, the equipment that they need are on site. We're slowly starting to ramp those back on site and get back to closer to full operations. Educational programs, though, remain remote. Our science center in tours are all shut down right now with no visitors on site and no oversight visits. All of the camps, all of the workshops, everything for the summer through August are now canceled or postponed. That includes the single dish school, which is currently rescheduled to October. The spring GBT training workshop has been canceled. And again, the next one will be in October. We've got the OSMA at 60 workshop is being rescheduled and looking at 2021. And the Argus 144 workshop will be held in the fall, but it's going to be held as a remote workshop. So it's going to be completely online. Like most sites, all of our summer interns, all of our RUs, all of those folks are going to continue to be employed by us, but they will be working remotely. None of them are coming on site at all this summer. And then the last bit under the educational parts, our 20-meter telescope, it is under repair. We're slowly bringing it back up, and hopefully that will be online within the next couple of weeks. We're waiting on some good weather right now to finish the work on that, and that will allow for increased educational programs remotely. Other good news is many of the operations are continuing to move forward. So the GBT proposals moved forward. There was no delay whatsoever in that process. The TAC simply met remotely. All of the proposal reviews are out and all the dispositions have been sent out, so you should have received it. For anybody that's curious, you can get into the details of that on our website, but the big picture is shown right here on this plot. So this is a plot showing the oversubscription rate for the GBT based off of the proposal grade, so looking only at those proposals that received an A ranking, and then also looking at all those proposals that received either an A or a B ranking. I'm going to emphasize this is only for those proposals looking at the open skies time, so applying to use the NSF-funded open skies time on the telescope. We further broke it down into two categories, one of which is just all proposals that we received, and the other one is the high frequency proposals. where high frequency is defined as those proposals that need the best weather conditions on site. So W-band, K-band near the water line, things like that. So the oversubscription rate was fairly typical for what we've been seeing. If you look at all A and B proposals, it's an oversubscription of around 3. If you only look at the A-rank proposals, it goes between about 3.5 to a little over 5, depending on whether you're looking at high frequency or all the proposals. Other things going on site, we do have a community survey underway. Many of you on this call have probably already received an email about that. This is a chance for us to reach out to the community to learn about your priorities and your concerns with both all the GBT observing and the data reduction tools that we have and the processes. So I strongly encourage all of you to go, if you haven't already, and fill out the survey. It's going to help us decide where to put our resources and our efforts moving into the future. So if you don't fill this out, we're not going to know your thoughts on where you feel like we should be going and where we should be focusing our efforts. Also going on with all of this, because of the changes in maintenance that we've had, we actually have more GBT time available than we had anticipated when we went through the 20A proposal process. As a result of that, we do have an open DDT proposal call. We've always had one open, but in particular, we're focusing on proposals that are at the low frequency and can be run as kind of filler projects. That is, they're willing to accept a lot of flexibility in their scheduling. There's a proposal call out online. You can see it. You can link it off of our main webpage there. But just to encourage those of you who have been thinking about a GBT proposal that's flexible, again, that preferably uses low frequency time, what we have a lot of right now, to please put that in. And again, this is because the changes with COVID have given us more GBT time than we had anticipated, and as we've had to reduce some of our maintenance activities. So with that, I just want to thank you guys again for coming to this talk. I'll pause for a minute here to see if we have any questions. Again, if you have a question, please put it in the Zoom chat. And if we, once we get through any questions we have, if there are any, we'll move on over to the exciting parts of the talk where you guys will get to hear a lot about Mustang-2. So I'll give just a pause here as people write their questions. So Ryan does want to remind everybody the survey has been sent out, which is what I said, the link was there. If you're interested in the link, just contact anybody at Greenbank if you didn't see it, and we can send it to you. So with that, I'm now going to hand this over to Brian Mason, and he will talk to you guys about the Mustang-2 receiver.
Thank you. Let's see, so I should be able to share screen. Is that working? Yep.
Yes.
Great. Okay, so thank you, Karen. I'm going to talk today about science with Mustang-2 with a couple of sidelights, and I'm not going to talk about the Siniavs-Zadovich effect because Charles Romero is going to talk about that next. So Mustang-2 is a 3mm bolometer camera that's been a shared risk instrument on the GBT since 2018. It has 215 feed horns with TES bolometers, and those together give it a 4 arc-minute instantaneous field of view and a 9 arc-second beam on the sky. Yeah. So the first science highlight I'm going to talk about actually came about originally from Mustang-1, the predecessor instrument to Mustang-2. And that is the discovery of unexpectedly sort of bright emission from thermal dust in the integral shaped filament in Orion. So this was a result first published by Scott Schnee and carried further by Sarah Sadavoy et al. And then when we were commissioning Mustang-2 a couple of years ago, we took another look at this source. We thought it would be a good commissioning target. And we also added GBT 1 centimeter photometry to that. And what that I can. What that showed, so the new observations were totally consistent with the old observations. And when we take the 3 millimeter, these two figures here show spectral energy distributions of two sort of chosen regions along this star-forming filament in Orion. And you see at short wavelengths a fairly typical kind of modified blackbody spectrum. But at 3 millimeters and now at 1 centimeter, we see a clear sort of what appears to be an upturn in that. So that was published this year in a paper that I led. You can look at the paper for more details about the interpretation of that. I'm also happy to talk about it. I think it's most likely, at least in part, because of a deviation from pure power law dust opacity. And that could have interesting implications for dust models and for how we infer physical properties of structures seen in the dust continuum in the sort of centimeter to millimeter, long millimeter range. So for instance, dynamical stability estimates of cores, star-forming cores, or filaments themselves. And this, on the left is the Mustang-2 map of the integral shaped filament. And just for comparison here, and to illustrate the power of big cameras on the GBT, I've shown the ALMA maps also at 3 millimeters. And so there's an ALMA 12 meter map, an ALMA 7 meter map, and then the combination of those two. So the total integration time was about 1/5. The GBT integration time was about 1/5 of what ALMA spent in total. And the reasons it looks so great is of course because we do have a large camera with 215 beams, and we have true zero spacing information, which ALMA does not currently provide in the continuum. The next science highlight I'm going to talk about is the star formation. I can't actually see this. Wait, sorry. The star formation radio survey. This is a survey that's been being led by Eric Murphy, and it's been going on for a number of years. It uses data from many instruments from the GBT. There are Ka band data going back nearly a decade in this survey. And then more recently, we've been using Mustang-2 to get 3 millimeter continuum imaging of galaxies. The goal of SFRS is to provide better calibrated and better understood relationship between star formation and radio emission. It's a sample of over 61 nearby galaxies. And so far, based on a couple of proposals of a pilot sample we put in last year, we've got imaging on 18 of them to date. And this shows an example. This SED in the lower right corner shows some of the power of this data is that it will really help you just disentangle, thermal dust emission from spinning dust in this case, from free, which is where most of the star formation signal comes from at these wavelengths. And this is just an example. This is NGC 6946. There we go. NGC 6946. There's an 8 micron IRAC image, and the green contours are the Mustang-2 data. And this is quite a big nearby face-on spiral. It's about 9 arc minutes across. And one interesting thing about this source is this region right here is actually the first known site of extragalactic anomalous microwave emission, first reported in Murphy et al. 2010 based on GBT 30 gigahertz observations. So that data is being analyzed, and once we get it written up and published, they plan to pursue imaging of the rest of the SFRS sample. Mustang-2 has also been used to do a pilot galactic plane survey. This was recently accepted into AppJ supplements as a paper and work led by Adam Ginsberg. And in the pilot survey, we have mapped 7.5 square degrees of the galactic plane to about 1 to 2 millijanskis per beam sensitivity. And these are just examples of those maps. It's not all of them, this is most of the maps. But the maps themselves are publicly available. And so one of the science results out of that is we in these maps, we find 10 hypercompact H2 region candidates, which have no centimeter wave counterparts. And by comparing this with the number of ultra compact, which is actually slightly less compact, H2 regions that do have centimeter wave counterparts, we can set a limit on the lifetime of the hypercompact H2 regions compared to that of the ultra compact H2 regions. So these are basically, we think these are the finding the very earliest stages of massive star formation of deeply embedded protostars, which are still very, very optically thick in terms of the H2 emission, the free. And finally, I'll just highlight another project. This is actually a project to map the thermal properties of the moon at 3 millimeters. This was led by Paul Hain. And this is shown here in the top left as an image of the moon at 3 millimeters made with Mustang-2 on May 15th, 2019. So just about a year ago, a bit over a year ago. And what you see at 3 millimeters is a combination of reflected sunlight and thermal emission, which is nicely illustrated by comparing the optical image to the right, which is actually taken on the very same night. So you can see, and then the bottom picture shows the 3 millimeter map high pass filtered. And by comparing these data with optical and longer wavelength radio data, they aim to measure the dielectric of the lunar regolith and constrain the rock size distribution. And just a side comment, this is not at present feasible with ALMA just because of the limit on the sizes of mosaics that you can do. So this is an area where the GBT really does some unique and cool things. And lastly, I'll just make a few comments on what I see as a potential role for the GBT in the era of ngVLA. For those of, many of you are probably familiar with ngVLA, but for those of you who aren't, it is a project to fund and build a large successor to the Very Large Array, an even larger successor to the Very Large Array in New Mexico, which is now going on 40 years old. The ngVLA design calls for 214 18-meter antennas with baselines ranging from 40 meters to 1,000 kilometers. And it also includes a so-called short baseline array of smaller antennas and 4 18-meter dishes operated as single dishes to provide larger spatial scale information. The ngVLA design emphasizes commonality of electronics and receivers to achieve low operations cost. But from the point of view of continuum science, total power antennas can often have a lot of trouble doing good continuum unless you have special sort of purpose-built receivers and electronics to do that well. This is indeed the ALMA experience. ALMA doesn't currently offer total power continuum just because the sensitivity is not quite what you'd want. But of course, we already have this capability on the GBT with Mustang-2. So I think in the future, the GBT could play a very valuable role in ngVLA with large format 1 centimeter and 3 millimeter MKID cameras. So I'll stop there. And I don't know if we want to take questions now or hand it straight over to Charles.
All right, if there are no questions directly for Brian, we'll go on to Charles, and then we can come back to questions at the end. So next we have Charles Romero talking, looking towards the future of Mustang-2.
Hello, everyone. Let's see. I think Brian has to stop sharing.
Did I? Oh.
All right, hopefully everyone can see the presentation.
Yes.
Great. So I will cover most everything SC related, that is Sunyaev-Zildovich effect. So I'll jump into what the Sunyaev-Zildovich effect is. It's basically just the inverse Compton scattering of cosmic microwave background photons. And there are several branches of SC effect. Those just come from what the different distribution of free electrons are and really their velocities or distribution of velocities. And primarily I'll be focusing on the thermal SC effect, which is proportional to the integrated electron thermal pressure. And here you see where Mustang-2 is looking relative to the spectral distortion we're interested in. All right, so I'm going to jump into galaxy clusters. That's because that's the prominent area where you get inverse Compton, where you have a large mass of hot free electrons. And so what do we want to get out of galaxy clusters? Well, one of the biggest drivers is constraints on cosmology. And on the right, you see potential constraints you get depending on different priors you have, that is, priors that determine the mass you're calculating for clusters. But that actually is the limitation of cosmological constraints from galaxy clusters, the precision and accuracy of mass we can get. So an obvious area to look to improve mass estimates is to go to higher resolution instruments than you have for survey instruments. And here I'm actually going to touch on early results from Mustang-1, the pilot instrument, that really highlight the strength of high-resolution SC cameras for identifying substructure. So the first one, Mason, 2010, that'd be Brian Mason, really showed that there was an enhancement in the southeast of RxJ 1347. That is, it confirmed this enhancement that had been seen loosely earlier. And then in 2011, Phil Koinga presents a paper on 4 clusters. And I think the highlight here is MAX 0744, shown on the bottom. We clearly saw a shock in that cluster, but it had been missed previously in X-ray data. When you go back and reanalyze the X-ray data, you see, in fact, there is a shock. And then Tony Marchowski also had a paper looking at MAX 0717 and used that to understand that there could be something going on rather dramatically with the different subclusters in that cluster. In fact, it was pretty obvious from other data sets there was a merger, but then when he looked at Bolocam, there's an inclination that there's residual kinematic SC effect. So beyond just looking at substructure, we also wanted to see what we could do with Mustang data in terms of actually calculating mass estimates. But to do that, we ultimately needed to combine our data with an instrument that had a larger field of view. So in the right here, I'm showing the field of view of Mustang-1 in the red, and Mustang-2 for reference is the blue dash circle, and the black is just our trajectory for a typical scan. Bolocam has a radius about twice of the Mustang-2 field of view. And that's important because that dictates the scales that you can recover for that instrument. And if you want to recover the pressure at large radii, you need that large field of view. So some early papers were developing the technique to recover the pressure profile. And then a 2017 paper I had looked at 14 clusters. And we constrained the pressure profile and looked at the masses we got out. but there wasn't any clear indication that substructure in the cluster that we saw with Mustang-2 had an obvious effect on the mass we recovered. Although one clear conclusion we reached with the 2017 paper was that Mustang-2 significantly increased our ability to constrain the slope of the pressure profile at small radii. And then 2018, I just checked that across various SC instruments, we find consistency because many results have been published without having such a check. But now I want to focus a bit more on the interesting thing that is our current instrument, Mustang-2. So a huge advantage is that we have a much larger field of view, more detectors and more sensitive. But here I'll look at the field of view. We can recover much larger scales than previously. Even better news, I would say, the Mustang team were able to produce a new pipeline that actually recovers scales beyond the field of view. And this seems to have worked out pretty well for this data set that we've gone very deep. I think for shallow data sets, it still has yet to be shown that we confidently recover these scales beyond our field of view. But for this paper that came out in 2020 this year, we're recovering scales out to 300 arcseconds. So that's almost 2 depths of range that we have good constraints. Beyond just producing a pressure profile, here's an image of the cluster for which that pressure profile came. Then we actually want to look at mass estimates that we get. So we did 5 different mass estimates. One of them is a hydrostatic equilibrium mass estimate, so we had to get electron density from X-ray. 3 are a YM scaling relation, and a third assumes the virial theorem. And overall, all these different mass estimates agree with past mass estimates in the literature, but it highlights that systematics are important, especially to account for differences where systematics hadn't been reported. And then I'll also note these black points are weak lensing, which shouldn't rely on the dynamics of the intercluster medium or galaxies. It should be an accurate measure of the total mass. We find that our hydrostatic equilibrium mass is close to what you get from weak lensing, at least this last point here. All right, so applying similar methodology from that one cluster to samples of clusters, one sample we have right now is looking at the mad cows, which comes from the WISE survey. And so a current paper in preparation looks at a sample of 16 clusters between redshift of 0.8 and 1.5. And one of the reasons to pursue these high redshift clusters is that the masses you get at these higher redshifts have a comparatively stronger constraint on cosmological parameters. But you do want to worry about how you've selected your clusters. So while there are surveys that select, there are SZ or X-ray surveys that are selecting high redshift clusters, mad cows is coming from infrared, so it has a different selection function. And you want to compare ultimately what you're getting from the different surveys. I should note this survey is ongoing. We now have 20 clusters, and given the multi-wavelength data sets, there's a lot to compare to actually understand the dynamical states of these clusters and what's going on. Another sample a bit smaller to start that has multi-wavelength data set is this Mustang-2 plus XXL, so XMM data set and hyper subprime cam study recently there was published a study that looked at 3 clusters all around redshift of 0.4, and they had different dynamical states. This is great that you can actually then compare to numerical simulations and see, do we find agreement with the signal boost you would expect in the SC or temperature boost in X-ray as you get from simulations. And we do find agreement. Furthermore, because you're combining SC and X-ray, you don't need to rely solely on spectroscopic X-ray temperatures, and you can even achieve better resolution when you're combining SC and X-ray. So ultimately, I think this paper really highlights the complementarity of the data sets used there, but in general, they're all complementary. Looking a bit more forward, we're looking to extend our analysis on the clusters Rookie 3146, and in particular, we want to look at pressure fluctuations. To do this, we want to ultimately calculate a power spectrum of residual pressure over average pressure. And the amplitude of that power spectrum will relate to the amount of turbulent pressure support there is, while the slope tells you about thermal conductivity. So the comment I made earlier about the hydrostatic mass being roughly that you get from weak lensing would suggest that we don't expect too much turbulent motion in this cluster, but we'll see ultimately what our analysis turns out. Then there's other physics we can look at in the intercluster medium beyond just turbulent motion. So one thing is to look at what the pressure is in X-ray cavities. These would be the bottom images here, for instance, MS0735, where we already have a nice data set from Mustang-2. And you see in a fraction of the time of Chandra, we get a pretty similar image. Beyond pressure support in X-ray cavities, we could also help with constraints on shock physics and heating mechanisms. Of course, you want to do this in tandem with X-ray, not solely SC, where looking at the low electron density regions is one of the best strengths for SC to help. Also with shocks, but less the heating mechanisms in more cosmic ray generation or particle diffusion, given that relics can be far out in the clusters, you want SC to probe those regions, again, which have low electron density, and X-ray studies might not find a shock. All right, and that's not a complete exhaustive list of the ICM physics that is probed with Mustang-2. Quickly then, I want to compare Mustang-2 to one of the other high-resolution SC instruments currently available, that being NICA-2. And to start, I give you just some sensitivity numbers that are given by both teams, and then what that corresponds to for a typical scan for SC studies. So for Mustang-2, we can do about 20 times 10 to the minus 6 in Compton Y for an hour. And NICA-2 comparatively would get 30. However, taking into account the beam sizes, we're actually doing much better than NICA-2. That is, we're mapping more than 4 times faster than NICA-2 when recovering the thermal SC effect. And then finally, I'll build on what Brian kind of had in his last slide, is just thinking a bit to the future. What could we do beyond Mustang-2? We could expand our field of view. That would obviously help in mapping speed and spatial scales recoverable. We can also expand the wavelength covered. I think going to a multi-chroic instrument is very desirable and feasible. We would also look to use a field array of microwave kids and then make them also polarization sensitive. So one thing thinking about SC is that does give you a bit of handle on the different SC effects available. And then it also would help with, say, point source subtraction. But many other advantages to going to a camera with more detectors and 2 wavelengths. So with that, I'll end and take questions.
So thank you, Charles. So if anybody has any questions for him, again, please type them up in the chat and we can read them out loud to everybody. And we'll just give a moment or two for people to type them up if they have them. Well, as people are thinking of them, I will remind everybody once again about our survey as well as our proposal call that's out there. So again, the survey is online, or just contact anybody at Greenbank to get that link. And we do have a DDT proposal call out for low frequency proposals. Looks like we don't have any questions, which means Brian and Charles did a fantastic job with this. So let me thank both of them again for their time with this. And thank all of you guys for your time and listening in, and hopefully getting inspired for our fantastic instruments. I do have one more question for you, which is to Charles or Brian, either one. What is the timescale for expanding the field of view for Mustang-2?
Currently, there isn't a strict timeline in mind. This isn't, the ideas beyond Mustang-2 are not concrete, but we obviously realize there are advantages to a future instrument. I'm not sure if Brian has a better idea of the timescale.
Yeah, no, I think that's a good summary. Probably the first step would be to explore the new detector technology, MKIDs, and there's work to be done there in terms of assuring you reach the sort of sensitivity that you want. That they're doing really well at the shorter wavelengths. There's still some work to be done at the longer wavelengths. Yeah, that's an active area, but there currently is no fixed timeline for an expansion.
Got a couple more questions coming up. The next one is, what is the science background for the moon observations?
Is there someone here who's better positioned to answer that than me?
I think you guys are on your own there.
So I can chime in. Simon Dicker here. There's several things. You can measure some of the thermal properties of the surfaces. You've got, what, 16 miles or kilometers? I'm going to get the units wrong. Resolution. Yeah. So, but there's also a lot, and you compare with other minerals and other wavelengths, you can actually start to make maps of the composition of the surface. So those are 2 of the things. Yeah.
Thanks, Simon.
Cool.
Next question. Yep. Sorry, go ahead.
No, I was just thinking that was my question there. Thank you.
Okay. So next question is, what is the major impact of the polarization for the SC work?
Right, I'll take that. So there is a polarized SC effect, but the signal for that is extremely weak, and we're just not even close to capturing that. Ultimately, the move for polarization in the detectors is not driven by SC science, but the fact that these are already being developed, and provided, I suspect it will be the case that that's not the limiting factor for sensitivity of kids, you might as well build that in, because there are other science drivers that do want to make use of polarization.
Yeah, in particular, thermal dust in the galaxy would be one target.
Okay, so I believe that's all of our questions. So thank you guys again for Brian and Charles for the talks, and thank everybody else for your time and attention for coming. So we very much appreciate it. Bye-bye.